Hey guys, welcome back. This will be the last new lesson that we're doing before spring break. So the next lesson after this, when we come back in person, we're going to do our M&M's lab. So we'll be referencing the M&M lab and this one here. And then we'll take our quiz in person the last day that I see you guys. And then, of course, we'll have spring break. Then we'll come back and we got, I think, one more chapter before we take the test over inference with proportions. So this is going to be about power and effect size. So if we look at this picture here that's worth 1,000 words over the whole hypothesis testing process, the first distribution is if our hypothesized proportion is true. So if the hypothesized proportion is true, then as we do millions of samples, it will slowly fill up all these possible sample proportions, will give us a sampling distribution model that will be centered at the true proportion, right? That's what we would expect. And whatever we set our alpha level to, the significance level, that's going to be the type 1 error, the probability of the type 1 error, which would be a false positive. Now, if the actual proportion, the true proportion, is not the hypothesized proportion, then we actually have a different sampling distribution. And as we do thousands and thousands of samples, it would actually fill in this sampling distribution model slowly, right? And then anything that was beyond that significance level for that sample size would be the correct decision, which would be the power of the test. The power of the test to be able to detect a difference between the hypothesized proportion and the actual true proportion. That's going to be this area here. Then anything that's below that significance level, that critical value that we would have, would be a type 2 error, which is when we failed to detect or failed to reject the null hypothesis that wasn't true. Now that would happen if our hypothesized proportion was pretty close to the actual, our hypothesized proportion is actually pretty close to the true proportion, which is what we call the effect size. The effect size is the difference between those two proportions, the hypothesized proportion and the actual proportion. Now, the further away the hypothesized proportion is, then the greater the effect size, the more the power of the test is going to be, even with smaller samples, because it's a bigger difference, right? So if you have a coin that's only slightly weighted, where if instead of 50%, which would be our hypothesized, it was like 55% heads, it's only slightly weighted, right? Then that wouldn't be a very big effect size. But if it was heavily weighted, where 75% of the time it would flip a heads, which I don't even know how that would be possible, but then it would have a really large effect size, and it would be very easy to detect that difference, which means we have a very large power of the test, even with a small sample. Okay, so let's talk about this. See how it would be nice if I could like move this around or something, or interact with that. I know. That's why I solved that problem. All right, so let's talk about, in our context, our M&M lab. So what we're going to do is I'm going to give you guys a bunch of fun size bags of M&Ms, and you're going to sort them out and find the number of orange ones we have, and then we're going to look at the proportion of orange compared to the total, which would be an accumulative running total of the proportion of orange as our sample size grows and we open more and more bags of M&Ms. And you guys at home will be able to do it too. You can buy any size bag of M&Ms, it doesn't really matter. And then I'll share the document, this Google Sheet, and you can upload your information and see everyone else's as we go. It'll be really cool. I'm excited about it. So the hypothesized proportion, by the way, M&M says that 20% of all the M&Ms should be orange. And we're going to be testing that claim. And I'm going to show you in just the next slide the results we got from last year, and we'll see if we can get similar results this year. It's going to be pretty interesting. But the first thing we want to do is select an alpha level. So the alpha level is going to be the probability that we have a type 1 error, right? That's this part here. So if it actually is 20% orange, this is going to be the proportion of samples that we have a false positive, where we accidentally reject a true null hypothesis. So are we okay with being wrong and calling out Mars and Mars on their BS 1% of the time and being wrong, false positive, or being wrong 5% of the time with a false positive, or incorrectly rejecting null hypothesis 10% of the time? Now, since we're dealing with candy, I'm okay with a pretty sloppy alpha level of 10% because it's not really that big of a deal. But typically we default to 5% and 1% for really serious cases. So whatever we set this alpha level to, which we're going to do 10% because it's just candy anyway, then that is the probability that we would be wrong in rejecting a true null hypothesis, which is a type 1 error. So here is a scatter plot of our data from last year, which is pretty cool. The total amount of M&Ms that we sorted collectively as a class was 783, and the sample proportion we got at the very end was 26.4%. In fact, it kept getting worse, and the last proportion we had was the highest proportion. And the law of large numbers tells us that we would expect it to approach or converge to the empirical probability as our sample size increases to infinity. So what that means is that the margin of error is going to shrink. And so I actually graphed out the margin of error. This is how I put it in the calculator, by the way. It's kind of cool. 1.64, which is our critical value for a 90% confidence interval. Because we're doing a two-sided test, a 90% confidence interval would have 10% error on both sides, right? That's left over. And so that would be our significance level at that point. So critical value of 1.64 times the hypothesized proportion. Ooh, that should actually be 0.2. Sorry, because that's the probability. It's not going to change the results I got here, but we're expecting 20% orange and the hypothesized not orange of 80%, divided by x. Now, x was a variable that's graphed along the x-axis. That's our sample size. So as our sample size increases, what happens to the margin of error? It decreases by the inverse square root, or the reciprocal square root law, just like gravity, by the way. It's kind of cool. And so that's going to decrease. And what is going to end up happening is as soon as our proportions cross this line, they would be in the p-value that would make them significant, because they would be either in the top or the bottom 5%, which collectively would be a p-value of 10% because it's a two-sided test. So as we collect more and more data, and as you can see our scatter plot go up and go down, kind of or pretty volatile at the beginning, as soon as it crosses this line, we would be able to reject the null hypothesis. And after that point, it never went back to the point where we wouldn't have been able to reject the null hypothesis. So our first sample proportion was when we did a sample size of 285 that we were able to say with a sample proportion of 24.9% orange that we were able to reject the null hypothesis with a alpha level significance of 10%. And every value past that would have been able to do it as well. Now our final p-value, the probability of this occurring, we could probably actually calculate, but that I think it was like 1 in a million. So if there really was a true null hypothesis of 20%, then the probability of getting the value that we got was incredibly rare. So we believe we were onto something, and that there actually was a drastic overrepresentation of orange M&Ms for some weird reason. What happened last year is I had a bunch of M&Ms that were from Halloween, so they were branded from Halloween, and so we thought perhaps because they were branded for Halloween that they, even though it's not different colors like for Valentine's Day, which would be orange, white, and pink, even though, they were branded for Halloween in the packaging, right? So we thought maybe because it was Halloween, they increased just subtly, maybe by 5%, or our closest estimate was 20 or 26%, that they increased by 6% or 6.4%. The number of orange M&Ms in there, perhaps. So we actually redid this entire lab with another set of M&Ms that were not branded for Halloween that we got later, obviously. And then we discovered the exact same thing. There were still more orange M&Ms than we expected. And as we increased our sample size, the amount of evidence just kind of really was a nail in the coffin if you think about it, because our p-values kept getting more and more rare. So it was pretty substantial. So I believe that we'll actually have a sample size larger than this and p-values even more rare than that. So my question is, are we going to see the same thing this year, or was it just last year that perhaps they changed the proportion of orange M&Ms from what we expected? So anyway, absolutely fascinating information that we gathered from last year. I'm excited to do the lab again with you guys the first day we come back next week. And whether you're A group or B group, we'll still have the data and we'll be able to see how it grows with that Google Sheet. Then I'll have that data forever. Oh, I'm so excited. It's going to be a lot of fun. All right, so let's get into this again. So here are our hypothesized proportions. So we're hypothesizing 20% orange M&Ms. Now with a sample size of 175, we had a standard deviation of about 3%. So if I have an alpha level, which we set our alpha level, it would be 5% because we're actually doing a two-tailed test, but it's a little confusing. So we're going to put it at 5% because we actually have 5% on both sides. So yeah, just kind of roll with me on that one. So if we set the alpha level to 5%, then whatever the true proportion is, this is, it's not actually 20%. I don't think it is 20%. So if the true proportion of M&Ms that were orange was 23%, then this would, down here would be the power of the test, our ability to be able to detect that difference, which doesn't look very high. It looks like maybe about 30% or 25% of the time we would have been able to detect it. But as the true proportion is different, say it was actually 20%, 26%, which was the best estimate that we had with our largest sample size of 800 and whatever it was, then you notice the power of the test, because it's actually following, not centered at 20%, but the actual distributions would be centered at 26%, even with a sample size, a small sample size of 171, which would be maybe about, let's see, maybe about 10 bags of fun-sized bags of M&Ms, which isn't really that many, we would have been able to detect that proportion difference more than 60% of the time, it looks like. But maybe about 40% of the time we wouldn't have been able to detect it. So what I'm showing you here first is the power of the test, the effect size, and how that impacts the power of the test. So the power of the test is the sensitivity of the test to correctly reject the null hypothesis, to be able to detect the difference. That's the power of the test. Kind of cool. And it even kind of makes sense of how we would use that word in English. Then the effect size is the difference between the hypothesized proportion and the actual proportion. Now, if the actual proportion of orange M&Ms was, say, 30%, then even if we had a really sloppy alpha of like 20%, which would be 10 on each side, then 90% of the time, even with a small sample size of 171, we would have been able to detect that difference because it was such a large effect size of a difference between 20 and 30%. So let's go back to the 26%. And let's say we did have 10% alpha, so 5% on both sides here. Let's say we wanted to be able to detect it more. We wanted a more powerful test. Well, one of the ways we can do that is by increasing the sample size. So what happens when we increase the sample size? Well, by the inverse square root law, it's going to decrease our margin of error, just like we saw here. So, didn't mean to do that. So as we increase our sample size, the margin of error is going to decrease. So by the time we got up to here, we had, if we quadruple the sample size, we cut the standard deviation in half, which I think is close to what's being shown here. So now centered at 2%, this is the actual distribution of sample sizes of 781 instead of sample sizes of 171. So this is the actual distribution we would expect, and we'd have the exact same thing over here as well, centered at 26%, if that actually is the true proportion of orange M&Ms. Now our alpha level of 5%, 10% on 5% on both sides of 10%. Now the power of the test looks closer to 90% compared to what it was before, whenever we didn't increase the sample size. So when we did increase the sample size, we had a power of the test of about 60%, but once we've increased our sample size, almost quadrupling it and cutting the standard deviation in half, now the power of the test went up from about 60% to about 90% of the time we'd be able to detect it, maybe 95%, it looks like, close to. And then the type 2 error probability of not being able to detect it would be down to maybe about 5%, and our type 1 error still would be the same at about whatever we set it to, about 10%. Which is really cool. So how do we increase the power of the test without changing the effect size? Because the effect size is fixed. It's whatever the difference is between the hypothesized and the actual true proportion, whatever that difference is there. Well, the best way to decrease both types of errors would be to increase the sample size. Now, you're technically not decreasing the probability of the type 1 error, because that's set no matter what. That's whatever your alpha level is. But the probability of the best way to decrease the type 2 error and also increase the power of the test for whatever effect size we have is to increase the sample size. So absolutely fascinating stuff. I hope you guys enjoyed that. And let's move on to the next part. I don't need to show that. Okay, so the power of the test, the probability that the null hypothesis is correctly rejected. So it's the sensitivity of the test, in other words. The power is 1 minus the beta, where the beta in this case is the probability of failing to reject. So the alpha level is the type 1 error. The beta is the type 2 error, in other words. So 1 minus whatever the beta value is going to be the power of the test. Now, the only way we can actually calculate the beta value or the power of the test is to know the true proportion, which we can't really know the true proportion, just like the Las Redes Reef example. We can get it within the margin of error, so it's rare that we actually truly know the power of the test or the type 2 error. All right, so as we increase the alpha level, then we also increase the power of the test. So as we allow for a less critical alpha level to be able to detect it, so smaller burden of proof to be able to call BS on the null hypothesis, that increases the power of the test. So you see, as we decrease that, the power of the test goes down. Okay, so basically there's a direct trade-off between having a powerful, let's say, powerful judicial system that's able to lock away guilty people, and the amount of innocent people we lock away as well. And as we increase our burden of proof, like beyond a reasonable doubt, it decreases the power of the test. So there's a trade-off, a direct trade-off between the power of the test and the alpha level that we set. Okay. The other thing we can look at is as the probability of having a type 1 error, which is the alpha level, increases, then the probability of having the type 2 error is going to decrease. So that actually is an indirect relationship. I need to fix that. See if I can fix it real quick. So as we increase the probability of type 1 error, we decrease the probability of type 2 error. Okay, so if you notice, as the type 1 error increases, the type 2 error decreases. So it's a more sensitive test, right? It is a more sensitive test, meaning it's more capable, more powerful to detect it, but we also have more false positives. So there's a direct trade-off between our two types of error. So as we increase the sample size, that decreases both types of error. I don't think that's actually correct, because we would actually end up moving the alpha level as well. So the type of error that it actually decreases would be the type 2 error. So our type 1 error is always set to our alpha level, which would just decrease as we decrease the sample size, or increase the sample size to decrease the standard deviation. So it actually would only decrease the type 2 error, but also increase the power of the test. Then the effect size, so that's our different sample sizes. The effect size is going to be the offset between the true proportion and the hypothesized proportion. So the further off that is, so if it's just barely above the hypothesized proportion, then we're not going to have a very powerful test unless we really increase our standard deviation, or our sample size. Then we might have a slightly more powerful test. But if they're really close to each other, we're going to have a really large sample size in order to be able to detect it. So we really want a larger effect size. So the further away those two are from each other, the effect size, the more powerful our test is going to be. All right, so let's look at the homework, number 28, Alzheimer's. So testing for Alzheimer's disease can be a long and expensive process, consisting of lengthy tests and medical diagnosis. Recently, a group of researchers devised a 7-minute test to serve as a quick screen for the disease and for a use in the general population of senior citizens. So they can actually test more people if it is quicker and costs less. So we can actually detect more people that might potentially have Alzheimer's, and then those people we can do the longer, less sensitive test, but the one that's more accurate and a more expensive process. Okay. So more powerful tests are more accurately able to correctly diagnose whether or not they have Alzheimer's. So it has less type 1 and less type 2 error. So a patient who tested positive would then go through a more expensive battery test for medical diagnosis. The authors reported a false positive rate of 4%, so that's the alpha level is 4%, okay, and a false negative rate of only 8%. So that means there's only 8% of the false negative rate. So the distribution would look like this, which is kind of cool. So put this in context for the hypothesis test. What is the null and alternative hypothesis? So the null is going to be like the status quo, which is that they don't have Alzheimer's. So that's that they don't have Alzheimer's. The alternative, which we're trying to prove, is that they actually do have Alzheimer's. So they do not have Alzheimer's until we're able to prove that they do have Alzheimer's. 4% of the time we would have a false positive, where we claim that they had Alzheimer's when they actually didn't, so that would be a false positive. And then 8% of the time we fail to detect that they actually had Alzheimer's, which is kind of a big deal if we're trying to help people find treatment for Alzheimer's. All right, in this context, describe a type 1 error and a type 2. Okay, well, I kind of just did that on the last one, but I'll say it again. So a type 1 error would be a false positive, which is that we said they had Alzheimer's when they actually didn't. So we thought they had Alzheimer's, but they didn't. The type 2 error is failing to detect that they have Alzheimer's. So that would be basically failed to detect they had Alzheimer's, exactly what I just said. All right, which is worse in this context, a type 1 or a type 2 error? Explain. So would we rather have a false positive or a false negative? So in this case, I would say it would be worse to have a type 2 error, because we would rather know that somebody had Alzheimer's than not know. And then even if they was a false positive, we would just end up spending money doing a longer test and screening to see if they actually did have Alzheimer's. So that would waste some money, but at least there wouldn't be a lot of seniors that are out there with Alzheimer's and that they didn't know, so we couldn't seek treatment. There's no cure for Alzheimer's, but there's medical treatment and of course better understanding for their family as well as they go through that process. So which is worse? I would say type 2. In this case, failing to detect that they had Alzheimer's. So we really want a more sensitive test that's cheaper. I think that would be beneficial, even if it had more false positives. That would be okay as long as we did a follow-up test. So what's the power of the test? The power of the test is going to be the ability for it to detect it. So that's going to be 1 minus the type 2 error, or beta. In this case, they said it was 8% for the beta, so there would be 92%. So of all the seniors that have Alzheimer's, 92% of the time we would have been able to detect them. So and of all the seniors who didn't have it, which would be this one, we would be able we would only have a false positive rate of 4%. So of all the people who didn't have it, 4% of those we would accidentally say that they did when they didn't, which is kind of annoying. But of all the people that did actually have Alzheimer's, 92% of them we would have been able to accurately detect it. So the power of the test would be 92%. So if somebody says a test is 92% accurate, there's actually 92% accurate in detecting it, or 92% accurate in not detecting it, because there's really two different distributions going on. There's two different cases, right? You either have it or you don't. What's the probability that it correctly detects it, which would be the power of the test? Probably what they're referring to when they say it's 92% accurate. But then the false positive rate would be something different. In this case, it was a 96% that it would be able to detect that you didn't have it. But then, of course, 4% of the time it would have given a false positive. So if you could, would you prefer a more powerful test than that produced more false positives? So more powerful tests that produce more false positives. So more false positives would be moving like the alpha level this way. So it's a sloppier test when it comes to false positives, but it would be a more sensitive test to be able to detect it. So that means there would be fewer that fell through the cracks. So there would be more seniors that didn't have it that would just kind of be harassed by the having to go through the process, and maybe it would be a little scary to try to tell them, hey, we think you might potentially have it. There's actually a lot, I don't mean to bring this up, but there's whenever they do like prenatal screenings through like DNA of obviously prenatal, so I'm talking about infants, there are actually some tests that are very, very sensitive, but they also have a lot of false positives. And somebody that I knew, they thought that their child had the potential of having some sort of genetic disorder, and luckily it was not true. It was a false positive, but that's not cool. Like that's kind of frightening to put a mother through that, and to have to try to prepare for raising a child with Down syndrome or some genetic disorder. So we don't like any types of error, right? We don't want to talk about that really, but when it comes to any type of testing, there's going to be this error. So if we could have a more powerful test that produced more false positives, but there were fewer people that had Alzheimer's that we failed to detect, then yes, we'd probably go with that because we were more concerned about the type 2 error. Okay, so just really good stuff. Honestly, this stuff applies to every type of testing, so really good information for you guys to know. So if you have any questions, please let me know. I hope you guys are enjoying this. I really am enjoying it. And it was really good to see you guys in person the last 2 days, and I'm looking forward to seeing the B students tomorrow. So I'll see you guys later.